derivatives. Chapter 2, Section 4, the derivative. This is what we really want to get to, is the derivative. 2-1, 2-2, 2-3, it's all background. I can't talk about a limit unless I explain what a limit is. I can't talk about rate of change unless I explain what it is. So all those sections were really to help us understand limits, understand looking at a function, knowing what it does, and asymptotes, vertical and horizontal. Now we can actually go into the derivative. Okay? So the concept of limits helps solve two basic calculus problems. Finding the equation of a tangent line to a function at a specific point. So if I had a graph and I pick a point at it, I can find the slope of that line by doing a derivative. That's one. Not going to be a major thing for us because slope of the tangent line was great and all, but we're trying to apply it. So what we're going to focus more on is part B. Part B is finding the instantaneous velocity of an object in motion, talking about rate of change, instantaneous rate of change. That's what we're going to do. So we're going to spend a little bit more time on B. So we're just going to get an introduction today. We're not really going to do too much of the problems, but I do need to talk about rate of change first. So on a trip, you pass a mile marker 120 on the interstate highway at 9 a.m. and pass a mile marker of 250 at 11 a.m. The average rate of change of distance with respect to time, also known as average velocity, is the distance traveled divided by the elapsed time. So if I wanted to find the average rate of change, I would take the difference in the miles over the difference in the hours, and that would give me the average rate of change. Okay, so let me back up a little bit, make sure we understand this, and put it to what we already know. So we're going to bridge algebra and calculus today. So you're told at 9 a.m., you're at mile marker 120. Then at 11 a.m., you're at mile marker 250. Okay? And I want to find the average rate of change. And what they did was 250 minus 120 over 11 minus 9. Let me stop there. Does this look familiar to anybody? Yeah. What is that? Slope, right? M equals y2 minus y1 over x2 minus x1. It's the same stuff. Calculus gets started, it's born from, it begins with slope. Because slope is how something's changing. Now, that gives us 130 over 2, which is 65. And more specifically, it's 65 miles per hour. Now, average rate of change means here's where I start, here's where I end. On average, I was going 65. Now, I could have been going 100 for the first hour, and then maybe like 50 or 45 the next hour, but on average it's 65. But this is average rate of change, okay? Now, I do want to take this concept a little bit further. If I call this x1, y1, x2, y2, you're like, I got it. What if I call this A, f of A, B, f of B? Would you be as comfortable to say f of B minus f of A over B minus A? Can we agree, or can we get to, that that's exactly the same thing? It's exactly the same thing, okay? So for now, y2 minus y1 over x2 minus x1 in function terms is f of b minus f of a over b minus a. So let's get us thinking from here to here. And then soon, I'm going to get you to another form of it that's basically the same thing. Okay? So, average rate of change, it's slope, we know how to do it, things are good. During this trip, it's likely that you vary speed from 65 miles per hour, sometimes faster, sometimes slower. Okay? Now, they give you this average rate of change, and it looks a little weird. So let me show you what they're getting to. Okay? So going back to our paper, are we comfortable with f of b minus f of a over b minus a. Are we okay with that? Not too bad. It's the same thing as y2 f of b, y1 f of a, x2 b, x1 a. You can see here how they match up, and they're the same. Okay? Now, they're coming across with something a little different. So what they're saying is the distance from B to A. So from 9 a.m. to 11 a.m. is how many hours? 2. Does everybody see that? From 9 a.m. to 11, it's 2. Let's call that H. 2 hours have gone by. How do you find H? You do B minus A. We okay? Now, instead of calling it B, you can call it f of A plus H. Now, let me explain that. You're like, why would you change that? Well, again, A is 9 a.m., B is 11 a.m. Are we okay? But if A is 9 a.m. and H is 2, what's 9 plus 2? That's B. Are we okay? So if you know how many hours have passed, if you take your starting point, A, 9, and add 2, you get to 11. So if you take your starting point plus H, that gives your ending point. Your ending point is B. So when they call f of B, f of A plus H, it's the same thing. You're starting plus how far you've gone. 9 plus 2 gives you B, which is your ending point, and minus f of A. This is the same thing as slope. It's just that's how we got it. So from now on, what you've seen, what we've alluded to, is f of A plus H minus f of A over H. What is that? It's slope. It's slope, it's slope, it's slope. That's all it is. Okay? But you go from there to there to there, and it's the same thing. And how does slope work? Starting, ending, find the difference, and you got your slope. Okay? So this is where everything begins. F of A plus H minus f of A over H. That's the average rate of change. Okay? Previous section, we called it the difference quotient. So we're going to start with an example. A company manufactures plastic planter boxes. The revenue generated from selling X of these boxes is given by the revenue, 20X minus 0.02X squared, but X has to be between 0 and 1,000. Find the average rate of change from the production of 100 planters to 400 planters. Now, I'm going to write all this out, and we're going to do it together. If you're still a little shaky of what I'm talking about, I'm going to put it all out for you. So, there's the revenue. And we want to go from 100 to 400. We want to find the average rate of change. Okay? So let's go nice and slow. How many planters are we starting with? How many planters are we starting with? Let's call that A. How many planters are we ending with? Let's call that B. We good? So if I was talking about a point, this would be 100, this would be 400. Again, going back to y1, y minus y2 minus y1 over x2 minus x1, it's just like that. But now we're calling it A, and we're calling it B. Now, how much revenue will I make if I sell 100 planters? How do I figure that out? Plug 100 in for revenue. So let's go to our calculator, go to y equals. In y1, we'll put 20x minus 0.02x squared and then if you go to the table feature, plug in 100, what do you get? What do you get? 1,800. Plug in 400, what do you get? 4,800. Okay? So, if you're still a little shaky, x1, y1, x2, y2. We're simply calling it A, f of A, B, f of B. Is everybody totally okay right now? The only thing I haven't mentioned is this thing called H. Okay? To find H, it's B minus A. So what's B minus A? 300. Stop there. Okay? Now, I'm going to put all three in front of you, and I'm going to prove that they're all the same. So the one you like, y2 minus y1 over x2 minus x1. I'm going to make it so you can actually see it too. Okay? There's the first one you like. Then I'm introducing f of b minus f of a over b minus a. Then I'm introducing f of a plus h minus f of a over h. And my job is to show you that they're all the same. But this last one is what we're going to lean towards. F of a plus h minus f of a over h. So we're going to do all of them. We're going to do every single one. Okay? What's y1? Be careful. I'm saying it wrong. What's y2? Thank you. You listen to the question. What's y2? 4,800 minus y1? 1,800 over what's x2? Minus what's x1? So that would be 3,000 over 300, which would be 10. 10 over 1. Does everyone see how I did that? Slope, same stuff, done slope a million times. Now, what's f of b?
4,800.
4,800. Minus, what's f of a? 1,800. Over, what's b? Minus, what's a? Oh my gosh. Same thing. Again, you're going from A to B, you're going from 100 to 400. This last one is f of what's A? 100 plus what's h? Minus f of what's A over what's h. Okay? Now, I'm filling it in totally so you can see where things come from. Okay. What's 100 plus 300? It's the same thing. And what's f of 400? What happens when you plug in 400? You get 4,800. Minus what happens when you plug in 100? You get 1,800. And the bottom's 300. You still get 3,000 over 300, which is 10 over 1. So all I'm trying to show you is that they're the same. They're the same, they're the same, they're the same. But we're going to start leaning towards the last one. But all it is slope. And instead of saying the word slope now, we're going to say average rate of change. We're going to say average rate of change. We okay? So trust me, or I'm proving to you that it's just slope. It's just another way to look at it. It's just another way to look at it. So going back to our example, if we plugged in R400 minus R of 100, we got 4,800 minus 1,800, which is 3,000. And then on the bottom, we do 400 minus 100, which is 300. We get 3,000 over 300, which is $10. It's $10 per plate. $10 per. Okay? And you're like, all we're doing is slope. You're totally right. Now, what we did was if I graphed this function, it would look like this. I took a point here, I took a point here, and I found the slope of the line, which is the rate of change from here to here. That's what I did. That's what we all did. Okay, so graphically, that's what we did. And the line connected was called the secant line. The average rate of change of the reference between points is the slope of the secant. Okay? So a small steel ball is dropped from a tower and will fall a distance of y feet in x seconds, approximated by the formula f of x equals 16x squared. We'll start with writing that. What I'd like you to do, well, first of all, let's just look at it. So this is the tower piece set. At 0 seconds, if I plug in 0, 0 squared, 0 times 16 is 0. It hasn't moved at all. It's 0 feet away from me. 1 second later, 1 squared is 1, 1 times 16. 1 second, it's now 16 feet away from me. Plug in 2. 2 squared is 4. 4 times 16 is 64. It's now, 2 seconds later, it's now 64 feet away from me. And if I plug in 3, it's 144 feet away from you. Okay? So the moral of the story is, I don't know why you're dropping a small steel ball from the tower piece. Okay? If I plug in numbers, that's what you get. What I want you to find is the average velocity from 2 seconds to 3 seconds. So here's the function. I would like you to find the average velocity from 2 seconds to 3 seconds. Okay? And I'm going to ask you to do f of b minus f of a over b minus a, and the one we're trying to get to, f of a plus h minus f of a over h. So I'm going to get you started. I'm only going to get you started. Okay? Our starting point is 2 seconds, A. Our ending point is 3 seconds, B. I'm only going to get you started. F of what's B? 3 minus f of what's A over what's B? 3 minus 2. Now, to figure out f of 3, what does that mean? Plug in 3, that's what f of 3 is. Plug in 2, that's what f of 2 is. But don't do anything yet. I'll give you some time. At the same time, I want you to do f of what's A? 2. Plus. Now h. H is the distance from 2 to 3. So what would h be? 1. 1 second. Great way to say it. So this would end up being f of 3 minus f of 2 over 1. So I want to give you some time to do both sides so you clearly realize it's the same thing, it's the same thing, it's the same thing. Let's start leaning towards the second. Take your time, because it's really important that you understand that it's all the same stuff. cell, if you plug 3 into the function, what do you get? 144. Minus if you plug 2 into the function, what do you get? And 144 minus 64 is it? 80 over 1. And is that second per feet or feet per second? Feet per second. Okay? Feet's on the top, seconds on the bottom. Does everyone understand the left side? Okay? So if you took 3, plugged it in, 3 squared is 9. 9 times 16 is what? 144. That's what f of 3 means, right? Plug in 3 to the function. And if you need me to show you, if I go to y equals, type in 16x squared, if you plug in 3, you get 144. If you plug in 2, you get 64. That's where those numbers came from. F of 3 means plug in 3, it's 144. F of 2 means plug in 2, you get 64. 144 minus 64 is 80 over 3 minus 2. Are we okay? Now on the other side, f of 3, 144. F of 2, 64. Over 1, you still get 80 over 1, which is 80 feet per second. And this is called average rate of change. And really, it's just slope. It's just slope, it's just slope. Question?
So for the second formula,
yep.
Is it just taking a step back?
That's a great question. I would say the left side is the perspective of I'm starting at 2 seconds, I'm going to 3 seconds. Starting to ending, 2 to 3. The right side is the same exact thing, but instead of saying 2 to 3, I'm going from 2 seconds to a second later. Well, what's a second later? 2 plus 1 is 3. So it's the same thing. Going from 2 seconds to 3 seconds, or going from 2 seconds to a second later, is still going from 2 to 3. It's just a way of saying it, right? So am I going from 2 to 3, or am I going from 2 to a second later than 2? It's both 2 to 3. But we like this one because this formula is going to be the beginning of our calculus stuff and beginning of taking a limit and all that stuff. But it's the same. It's the same, it's the same, it's the same, it's the same. But sometimes it takes a little bit of practice to see it. Okay? So that's at 80 feet per second. And this introduced that plus h, which we did. Okay? Now, find the limit of the general expression for the average found in the previous slide as h approaches 0. So basically, if I take 16x squared, and this is where we're going to kind of work today. (16x squared), okay, and I want to plug it into this function. And we've been playing around with this a little bit, but now we're going to actually do it. Let's go through this nice and slowly, okay? What do I mean by that? Let's just, I'm going to do a different color. Let's just do this part alone, okay? If this was f of 3, you plug 3 in. If this was f of 2, you plug 2 in. What am I plugging in? A plus h. So where there's an x, what am I putting in? A plus h squared. Okay, this is where we got a little confused last time, but this is the beginning of it all, why algebra is so important. Okay? If I fill into this formula, which tells me average rate of change, f of a plus h says go to your function where there's an x, instead of plugging in 3, instead of plugging in 2, what am I plugging in? A plus h. Oh, it's right there. So again, if this was f of 3, you would do 3 squared times 16. I'm doing a plus h squared times 16. So this part is this part. Okay, I'm going to use a totally different color. Minus let's do this part. Go to the function, but instead of x, what am I going to plug in? A. So this is going to be 16a squared. That's that part. All over what? H. This is my original function. And let's do some algebra, okay? If I was going to clean this up, hopefully everybody knows that a plus h squared is a plus h times a plus h, which is a squared plus ah plus h squared, which is a squared plus 2ah plus h squared. Is everybody okay that this is all this? I don't have to work that out, but I think it helps people. So all of this becomes a squared plus 2ah plus h squared minus 16a squared all over h. Now again, what's scary about this is the algebra, but I'm hoping it's not that scary. Okay, if I continue to clean this up, spread out the 16, 16a squared plus 32ah plus 16h squared minus 16ah over h. And we've done touches of this. What ends up happening? 16a squared minus 16a squared goes away. We're left with 32ah plus 16h squared over h. You okay? What can I do to the top? Factor out an h, which is move 32a plus 16h over h. And then what happens to the h's? H over h is 1. It simplifies to 32a plus 16h. Algebra, 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 algebra. Okay? Now at this point, what the heck is that? 32a plus 16h. Well, what we're going to do is, you saw how I got 64 plus 16h. And then we're going to plug 0 in for h and see what happens. So this is going to get added to the limit as h approaches 0 of 32a plus 16h. And you're like, limit's going to come into this? Yeah, that's why we spend so much time on limits. And I'm going to plug 0 in for h. And I'm going to end up with 32a. And you're going to say, what the heck is that 32a? Okay? And what that is, this ends up being my derivative function. So, let me break all this down again, but I'm going to avoid the algebra. So what I wanted to do for you was to focus on the algebra in this example. So does everybody see all the algebra that I did? Everyone see all the algebra that I did? How I got this crossed out, we end up with this. Okay? So I'm going to repeat this but I'm going to forego all the algebra. So if I have the function 16x squared, that function will tell me if I drop a ball, how far is the ball from me? If I drop a ball, how far is the ball from me? But it doesn't tell me how fast that ball is going. It does not tell me the rate of change of that ball. If I wanted to find the rate of change of the ball, I would have to take the derivative. So I'm going to do this again without the algebra. I'm going to change the variables a little bit. To find the derivative, you take the limit as h approaches 0, f of x plus h minus f of x over h. This is your derivative function. This is the formula that will change everything to a derivative. So I'm going to go through this again, nice and slowly, but avoid the algebra, and then you're going to see, hopefully, the light at the end of the tunnel. Okay? The limit as h approaches 0. This tells me go to the function, but instead of x, what am I going to put? X plus h. Now, I changed it to x instead of a because a was kind of talking about the last problem. This will help me find anything. And it's tied to the function. So go to your original function, instead of x, plug in x plus h. Then minus f of x. Well, f of x is just the original. So minus the original. Stop there. Stop there. Okay? Now, trust me, algebra. This becomes x plus h times x plus h. You clean it all up. We already did all this, but I'll do a condensed version of it. Again, I don't want to do the algebra again. If you did x plus h times x plus h, you'd get all this. Are you with me? I don't have to do that every single time. And then the limit as h approaches 0 distributes 16x squared plus 32xh plus 16h squared minus 16x squared over h. Again, same algebra, I'm just not explaining it anymore because I already explained it. You see that this goes away, this goes away. Which leaves us with limit as h approaches 0, 32xh plus 16h squared over h. Then we factor out h. H over h is 1. And I'm going to stop there. Now, hopefully you're saying, it's the same stuff we just did. It's the same stuff we just did. Totally correct. Instead of a, I'm putting x. Instead of a, I'm putting x. But here's what we're trying to figure out. I wrote limit as h approaches 0 every single time. Every single time, every single time, every single time. And the reason why I'm writing it every single time, can I plug 0 into the first one? Nope, undefined. Can I plug 0 in here? Nope, undefined. Can I plug 0 in here? Nope. I can't plug in 0, until I get to this. Once I get to that step, can I plug 0 in for h? Yeah, so I don't write the limit anymore. And what's 16 times 0? So what am I left with? Now, all that work to get 32x. All that work to get 32x. And I put this little apostrophe. That little apostrophe means derivative. So all that work for 32x. Well, my original function was 16x squared. This one tells me how many feet the ball is away from me. So if you put in 1 second, the ball's 32 feet away from me. If you put in 2 seconds, the ball's 64 feet away from me. What does this tell me? This doesn't tell me how many feet the ball is away from me. This tells me feet per second. This tells me velocity. So the original tells me how many feet away. This one tells me rate of change. And it tells me something called instantaneous rate of change. Right now, at a certain second, how fast it's going. And let me tell you the difference. Take 2 and plug it in here. 2 squared is 4. 4 times 16 is 64. At 2 seconds, where's the ball? 64 feet away from me. Are we okay? Plug 2 in here. What's 2 times 32? At that moment, if I could freeze time, freeze that ball, how fast is that ball traveling? 64 feet per second. So this one tells me how far away, this one tells me how fast it's going. You tell me how many seconds, I'll tell you how many feet it is away, I'll tell you how many seconds. So if I was to put this in my calculator, 32x, you can plug in 1, 2, 3, 4. The first one will tell me how many feet away the ball is. The second one tells me how fast it's traveling. Are we okay? Now, you're probably like, oh no, my future is doing this algebra every single time. That is my future. Yes and no. You need to appreciate all this on the work it takes to get a derivative. But if any of you have taken calculus before, does anybody know how to get from this one to this one really fast? You remember anybody? So all this work, we got 32x. So if you're depressed and like, oh my gosh, we're doing algebra the rest of my life now, let me show you the shortcut. What's 2 times 16? And what's 2 minus 1? That's it. That's how you do all that work in 2 steps. 2 times 16 is 32. Subtract 1 from the exponent, x to the 1. Now, would you rather do all this work or would you rather do the shortcut? But the work proves why the shortcut works. So if this is intimidating to you, don't worry. I'll teach you the shortcut, but you should know both. Okay? And if you're really, really worried, doing all that work will probably be like a bonus or something, right? So, one big problem, then we'll stop. I have to get through some slides that are important. Don't get me wrong, they're important. But I don't want to spend too much time on it. An important slide is this. The limit as h approaches 0, f of a plus h minus f of a over h. That's important. That's what we just did. We just did that. We did the algebra version. I should give you a brief view. That's going to be our future. That's important. Now, this part is important, but not majorly important for us, because we're going to do a lot of application problems. So let me go through these slides and just get to the algebra stuff and we can practice. So in geometry, a line that intersects a circle at 2 points is called a secant line, and a line that intersects a circle at exactly 1 point is called a tangent line. So the 2-point thing is called the secant line. If it crosses only once, it's called the tangent line. The point of this is that the secant is average rate of change from P to Q. How did it change? The tangent line is the slope of the 1 point only, not from 2 to 3, just at 2. The idea from going from P to Q is average rate of change. The idea of just P is instantaneous rate of change. So we're going to use this in our work, but don't let it freak you out or worry about it. It's the same stuff we're talking about. Don't worry, it's where it all comes from. We're going to be using that formula, where it all comes from. The slope of the tangent line is the derivative. All of this is good. important stuff. Slope of the tangent line, instantaneous rate of change is the same thing. Velocity, same stuff. There's a process that we go by, but here's what I want to do today. Okay? Now, I'm going to do it with you. I will show you the shortcut at the end, but in order to get the shortcut, we have to do it the long way, so bear with me. Here's the big takeaway. Okay? Here's our original function. Here's our original function. And let's say this is like the distance of the ball. Same idea. This is the original, which tells me how many feet. This is the original, tells me how many feet, or this is like revenue, how much money you made. But it doesn't tell me how it's changing. So if I want to find the derivative, we use the limit as h approaches 0, f of x plus h minus f of x over h. Now again, I'm using x. The textbook uses a. It's the same idea. I'm just keeping consistent x, 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 x. Okay? But I want to go nice and slow because the shortcut is what you'll like, but I want to make sure we understand. So, limit as h approaches 0. This one tells me, go to my function, and what am I going to plug in? 16, where there's an x, what am I going to put? X plus h, plus 80. What am I going to put for x? X plus h, plus 6. Stop there. Does everyone see how I did that? For some reason, it just drives people nuts, and I know it looks weird, but all it's telling you is go to the function, everywhere there's an x, put an x plus h. Go to the function, everywhere there's an x, put an x plus h. Are we okay? Now, minus f of x. That's just the original, minus the original. And the last step, over h. Okay, so stop there. Ask me any questions. Any questions on where any of that came from? Now, the part that you should be great at, and why we spent so much time on algebra, is I'm going to skip some steps now. Not a lot, but some. Bear with me. Can you trust me that x plus h times x plus h is x squared plus 2xh plus h squared? Do I have to work that whole thing out? Do I have to type x plus h times x? You guys are good at it, right? I'm just going to rewrite it. Definitely show this to your friends. You can say, look how smart I am. This is the stuff I'm doing in college. Okay? And then if your friend is taking calculus, like, that's just algebra. You haven't even done the hard stuff. All right. So limit as h approaches 0. Again, this is all algebra. Negative 16x squared minus 32xh minus 16x squared plus 80x plus 80h 6. This is the part that intimidates everybody, right? But it's just algebra, it's just algebra, it's just algebra. Now, once you get to this point, it's downhill. People make little mistakes with the signs. People make little mistakes with the multiplying. Just be careful. But once you get to this step, good things happen. What happens? One cancels. Negative 16x squared, negative 16x squared. 80x, 80x. 6 and 6. Fantastic. So now we have limit as h approaches 0. negative 32xh minus 16h squared plus 80h over h. Now stop here. Just make sure we're all caught up. And I have written every single time, limit as h approaches 0, limit as h approaches 0, limit as h approaches 0, because every single time, if I plugged in 0, it's undefined. If I plug in 0, it's undefined. But at this step, what could I do to get rid of that h on the bottom? What are we going to do? Factor out an h. And I do that because I can't plug in that 0 because there's always an h on the denominator. There's always an h on the denominator. But finally, what ends up happening? H over h is 1. And because that h cancels, I'm showing a little bit more work than I really need to. Finally, can I plug in 0 for h? Finally, I can plug in 0 for h. I do not have to write the limit down anymore. And I get negative 32x plus 80. That is my derivative function. Now, all that work to get the derivative function. My original function will tell me like how many feet the ball is or how much money revenue I made. The derivative tells me how it's changing. The derivative tells me how it's changing. Now, look at that massive amount of work that you've just done. You've just done a whole page of algebra. And we talked about limits before, so you know what the limit is. That's a lot of work. You with me? So because of all that work, I can now show you a quick shortcut. Ready? Here's the original. The exponent goes to the front. Exponent goes to the front. What's negative 16 times 2? Good. Then you always subtract 1, from the exponent. What's 2 minus 1? Okay? Same process. What number is up here? What's 1 times 80? And then you always subtract 1. What's 1 minus 1? 0. No x's. Last part. What's the derivative of any number? 0. Let me show you why. Is there a variable here? If there was, it would be x to the 0. If there was, x to the 0. Because x to the 0 is 1. What's 0 times 6? So what's the derivative of any number? 0. So would you rather do this? Or would you rather do this? Okay, now that shortcut works because of all the work. Are we okay? So from now on, I can start using the shortcut. But I couldn't start using the shortcut until I show you the long way. And the long way involved limits. Couldn't talk about limits until we went over all those sections on limits. See how it builds? This is where things are going to get better now, okay, from chapter 2. But I needed all that background to get you here. Now we're going to spend time on application problems on how to use derivative, what derivative means, and all that. Are we okay? Stop there. So we finally got